Hello, and welcome to Section 3.9, Related Rates. Related rates problems are application problems that use the chain rule or implicit differentiation to describe how one thing is changing relative to another thing, and that other thing is changing relative to time. So the hard part about related rates problems is coming up with the formula or relationship between some of these related items. But there is a procedure that can help guide you. But you're going to need to review possibly some things from trig or from geometry, because you never know what kind of problem you might get. For example, you might need to remember how similar triangles work, or let's say the volume of a sphere or surface area of a sphere, things like that that you may not just have handy every day. So these are the steps to solving the related rates problems, and I'm not going to talk too much about them right at this second because I don't think it does much good unless you actually have a problem to look at. But with any application problem, always draw a picture if you can. Even if it doesn't seem like if it's one thing, like, a ball, or, it might be a man walking. How do you draw a man walking? Well, do your best to try to draw a scenario that shows how the things relate to each other. So let's look at an example. The surface area of a sphere is changing. And we're given that the radius of a spherical ball is increasing is 2 centimeters per minute. And we're asked at what rate is the surface area of the ball itself increasing when the radius is 8 centimeters. So we're being given a situation where we have a ball whose radius is changing, and we know the rate at which that radius is changing, and we're supposed to find the rate at which the surface area is changing. So you can see there's that dependency, that chain of dependencies. The surface area of the ball is dependent on the radius, and the radius of the ball is dependent upon time. The radius depends what time it is as to how many minutes have elapsed, because it's increasing by 2 centimeters per minute. So step one, draw a picture of the situation. So I'm not really, on a piece of paper, I'm not going to draw, I can't draw a three-dimensional object, a ball, but, this is kind of a cross-section, and you're just kind of think in terms of, okay, as the radius changes, the surface area is going to change, and the radius is moving outward, and after 1 minute, it increases by 2 centimeters. So if I use Desmos to continually increase the radius of this circle, you can kind of see how it's increasing and how the radius is going to affect the area of the circle, and if we were considering this in 3 dimensions, the surface area of a ball. So we've drawn our picture. Now what we want to do is find a formula or equation to relate surface area and radius. So the surface area formula for a sphere is 4 pi r squared. And notice that the sphere's surface area depends on the radius. So since we want the instantaneous rate of change of the surface area of the sphere, we want to differentiate this. So using the chain rule, we're going to be differentiating this. And we're using the chain rule because, remember, that radius is actually a function of time. And we want to find the derivative of s with respect to t. Now, there's no t showing up in this formula, but we know that kind of hidden within this radius is a function of t. So we're going to be using that same type of thinking we did with implicit differentiation. So the next step is, once you have your relationship, you want to differentiate. If you have an implicit or an explicit equation, it depends on how you differentiate. But in all cases, you're going to be using the chain rule at some point, whether it's, as just par for course for doing implicit differentiation, or if you have some other function, you just want to use the chain rule. Time is always your independent variable for the most part. So back to our problem here. So I'm going to find the derivative of the surface area with respect to t, and using the chain rule, I'm going to differentiate this as 8 pi r, that's the derivative of the outside, times dr dt, that's the derivative of the inside. So what do we do with this? Well, we were given that the radius is changing at a rate of 2 centimeters per minute. So, right, so that's dr dt. So I'm going to have to fill out dr dt and r in this equation in order to get my instantaneous rate of change of the surface area. So that leads us to step 4. State which variables and rates are known. And so like I said before, dr dt is 2 centimeters per minute. We were given that's how the rate's changing. And we were asked to find the rate at which the surface area is increasing when the radius is 8. So we're given that this r is 8. So we're going to, in step 5, plug in those values into our new relation that we've found the derivative of. And when I plug in dr dt is 2 and r is 8, I get 128 centimeters squared. 128 pi centimeters squared per minute. Let's look at another example. This time we're going to look at the rate that a distance is changing. So we have a man walking north at 4 feet per second from a point P, and then 5 minutes later a woman starts walking south at 5 feet per second from a point 500 feet due east. And we want to know what rate the people are moving, at what rate they're moving apart 15 minutes after the woman starts walking. So step 1, draw our picture, and this picture shows when the woman would start walking. So the man has that 1,200 foot head start. So that's what this shows. It shows that the distance between them, and by this line segment, points that represent the man and the woman. And this is going to be changing as this point moves south and this point. So if you set this up algebraically initially, you would have a vertical line segment at x equals 500 representing the woman's path, and the point as t moves, as time goes on this vertical line is x sub w, y sub w. And then the point tracing the man's path would be x sub m, y sub m. So let's look at what's happening here. What we're going to want to look at is how this line segment, the distance between these 2 points, or the length of this line segment, is changing when 15 minutes has elapsed. So that means that the woman's gone 4,500 feet in the southerly direction and the man's gone 4,800 feet north. So if we set the relationship between the quantities up, we want this distance, which we know is by the distance formula. So the distance between these 2 points as they move in their paths is given by the distance formula. Since the y values are all the only thing that's changing, and the distance between the points along the x-axis is a constant 500, this is a relation we have. 500 squared plus the difference between the man's y-coordinate on his path and the woman's y-coordinate on her path. So you can see that this gets kind of messy doing it algebraically like this, because the path of the man is actually given as a line with a independent variable of time, same as the path for the woman. And then putting that in the distance formula just gets kind of messy. So there's another way to look at it that would simplify things. So notice that as time goes on and the man and woman are moving apart, that distance between them is also the length of the hypotenuse of a right triangle, where one leg is that constant 500 feet them along the x-axis, and the other leg is actually the sum of the absolute values of the distance the woman is from her starting point and the distance the man is from his starting point. So instead of trying to create the scenario we had in the last slide with parametric equations of involving t and the distance formula, what we can do instead is set up as the relationship between the quantities as a right triangle using the Pythagorean theorem. So notice that now we don't have to have any equations of lines anymore. So our relationship is given by the Pythagorean theorem. This hypotenuse squared equals 500 squared plus this side length. And that side length, like I said before, is just the sum of the absolute value of the distances that each has gone on their path. So step 3, we want to differentiate the relationship that we found. So that's pretty easy. Differentiate this implicitly. Since 500 is squared as a constant, that term goes away. So we have 2d times dd dt equals 2l times dl dt. So what we're looking for is this quantity. So now step 4, we want to figure out what it is we're trying to solve for and plug in what we know. So dl dt is the rate of change of this side, and that's simply that can be determined from the rate of change of the way the man was walking and the way the woman was walking. So if I add the absolute values of each of their rates, so he was walking at 240 feet per minute and she was walking at 300 feet per minute, so this side is changing by 540 feet per minute. And then at t equals 15, which is the time that we're interested in, side L is going to be given by the distance that the man has walked from that t equals 0 time and the distance the woman has walked from t equals 0 plus this 1,200 foot head start that he had. So that gives us 9,300 feet. And then also at t equals 15, we can determine the length of the hypotenuse just by simply using the Pythagorean theorem. So notice I'm in feet per minute here. So then the last thing is to plug in the known values and the instant values. So plugging in my values of d and dl dt as well as L, I arrive at 539.22 feet per minute. And that is 8.99 feet per second. So that's the rate at which this point and this point are moving apart after 15 minutes. Now let's look at another example. And this example is going to involve similar triangles. So streetlights mounted at the top of a 15-foot tall pole, blue line, along the y-axis. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. So this little blue line segment's the man. And that segment is 6 feet tall. That's not changing. And it's moving to the right at 5 feet per second. How fast is the tip of his shadow moving when he's 40 feet from the pole? So the tip of his shadow would be the tip of that big triangle that's being formed by these black dots. So draw a picture of the situation as step 1. Label things. So I've labeled the man, the height of that blue segment 6. The rate is 5 feet per second. And I've labeled the man's position from the light as the distance x, and the length of the position that the tip of a shadow is, the distance the tip of the shadow is from the light by d. So here is the distance that the tip of a shadow is from the light pole, and here's the distance x that the man is from the light pole. So we can use similar triangles to find a relationship between d and x. So remember the ratio of the sides is going to be the same. So d over 15 is going to be equal to d minus x over 6. So there's my relationship that I'm going to differentiate, differentiating both sides implicitly. I have an expression, I end up with an expression in dd dt and dx dt. So dx dt is the rate at which he's walking, right? The rate at which his distance is changing from the light pole to the man. And we want to find dd dt. So step 4, we figure out what's known and unknown and what we want. So we want dd dt. And we know that dx dt is 5 feet per second. Oops, sorry. So plugging those in, combining step 4 and step 5, gives me 25/3 feet per second. So I am substituting with this dx dt, I'm substituting the value that I'm given, 5 feet per second, and I get 25/3 feet per second. So that's the rate at which the tip of his shadow is moving when he's 40 feet from the pole. So that's the rate at which this long side is moving, not the rate at which the shadow is elongating. So if instead we'd set it up another way, where we set up the relation x plus, if s is the length of my shadow, x plus s over 15 equals s over 6, then that's going to give me ds dt, meaning how long, the rate at which the shadow is lengthening. That's not the same thing as what they're asking for, which is the rate at which the tip of his shadow is moving from the light. But if we do solve this, we find that the shadow's lengthening at a rate of 10/3 feet per second, and his rate of 5 feet per second plus that lengthening shadow's rate of 10/3 feet per second does add up to the length, the rate of which the tip of the shadow is moving from the light. And now this last example says if the minute hand of a clock has length r, find the rate at which it sweeps out area as a function of r. So this time t is not our independent variable, r is. We want to find the rate at which the area moves, but instead of expressing something in terms of t, we're going to be expressing it in terms of r, though t still, is in the picture because things are moving relative to time. So if you draw a picture of the situation, what you're thinking of is the area of the segment of a circle and how that's changing as the minute hand moves along the circle. So remember the area of the sector of a circle with central angle theta. The area is theta over 2 r squared. So if you think about this is a generalization of the area of a circle, which is pi r squared. And of course the central angle of a circle is 2 pi. So there's our relationship. There's step 2. Step 3, we want to differentiate our relationship. So again, we are differentiating with respect to t, though our ultimate goal is an expression in terms of r. So dA dt is going to be given by d theta dt times r squared over 2, because our variable in this case is theta. Theta is what's changing with respect to time, not r. If you think about it, the length of a minute hand on a clock is not changing. It's constant. So now we need to figure out what d theta dt is. So if you think about it, the minute hand makes one full revolution around the clock, so that's goes through an angle of 2 pi radians in an hour, and there's 60 minutes in an hour. So d theta dt is 2 pi radians over 60 minutes, or pi over 30. So step 5, we're going to plug in pi over 30 into our differentiated expression. So dA dt is going to be 1/2 times pi over 30 times r squared, which gives me pi r squared over 60 centimeters squared per minute, or simply pi r squared centimeters squared per hour. So in summary, remember this 5-step process to help you. Of course, step number 2 and sometimes step number 4 are often the trickiest. So there are a lot of things that you're going to need to possibly brush up on geometry. That's a big part of a lot of these problems. And remember that sometimes it's easier to solve something geometrically, like with like with triangles, instead of algebraic equations.